Thank you. Actually, my other colleague Ravi Shankar was not able to come because he had some resident permit issues in Norway. So sorry for that. And thanks for voting for this talk so that it's here today. So this work is part of my PhD thesis. So I just wanted to share it with the telecom community. It's really helpful for mobile network operators, also everybody who is using a mobile phone. So you could learn like what can be done with mobile phones. Basically, me and Ravi are interested in this mobile networks and also devices, and particularly on the baseband side. I mean the radio communication protocol side. So we do a lot of baseband analysis, fuzzing, also try to analyze protocol messages, standardized protocol messages, also play with different phones, different vendors, different configurations, and all these things. We are also quite familiar with so many IMSI catchers and also IMSI catcher detection methods, wide variety of experience in dealing with these kind of devices and trying to play with them in practice also. So this work is kind of would be exploring something, a hidden side of operators, or hidden side of operators' devices, like how are their devices configured and what kind of new technologies are available. So all these things. So basically the talk is about, I'll just give some introduction about 4G LTE and then go about SON operations. SON is nothing but a self-organizing network. So which also reflects the title of the talk. Self-organized, nothing means like automatic. So we are trying to exploit some kind of automatic features that are installed in the mobile networks. And then I directly go to the vulnerabilities that we figured out, then what kind of exploitation methods we figured out, and the kind of setup we used, and all this results into some kind of denial of service attacks that really impacts both the customers and then also network operators, and what kind of impact this research generated and the status of these vulnerabilities, and then some takeaways in the end. Before going into the actual thing, just to give a brief idea about mobile network architecture. So almost this is similar in all kinds of generations. For example, like 2G, 3G, and 4G, it was almost similar. There were like slight changes here and there. But the basic architecture is like there's a radio network and there is a core network. So the core network is actually handling all the incoming traffic that's coming from the radio network. So core network is responsible for authentication, then starting encryption, then managing the user's subscriptions or authorizing and authenticating subscriptions. So all kinds of management is done in the core network. In the radio network, so basically this is nothing but a geographical area is kind of divided into cells, and each cell or maybe a group of cells are controlled by a base station. So in LTE, a base station is called, in technical terms, it's called as E node B. So sometimes in the talk, maybe I refer to E node B, but it's nothing but a base station. And we have the UE, it's nothing but cell phone, user equipment, and we have some kind of interface between the base station and the core network. This is a proprietary network, so I just named it as P. So then we have cells. So like I said, each cell or a group of cells are controlled by base stations. And something new which came up in LTE is called X2. So this is the interface that's connecting two base stations. So base stations in LTE can actually directly talk to each other, share configuration, share details, and do lots of stuff. For example, also handovers. Before going into the attacks, we discovered, I just wanted to give a recap of the different kinds of attacks that exist in telecommunication networks. So let's say this is a simple network, a simple hierarchy of the network. We have phone, we have base station, we have the core network, and that's how you connect to the internet. The first type of attack we see is nothing but IMSI catchers, also called as Stingray devices. These are quite popular, typically used for catching identities such as like IMSI. This is nothing but the SIM card number. Then also they used to do IMEI catching. So in the beginning this was the case, but later they also use this for voice interception, passive and active both. So basically, this is nothing but a fake base station that's impersonating a real one, and trying to attract mobile phones and trying to fetch or intercept data from them. This is possible on all three kinds of generations, like 2G, 3G, and 4G. And the second type was man in the middle. Although these attacks work only in 2G and partially in 3G also, so there's a man who is sitting in between the phone and the base station. So the over-the-air link is somehow taken over by a malicious attacker. Or let's say he's running a base station and trying to relay the traffic to the network. Sometimes it could be hard to relay voice calls because the man in the middle has to have some kind of connection with the network operator. So until he has that, he cannot relay the calls. SMS and these things can actually be routed. So the third type of attack is interception. So I call it passive interception. There's one guy sitting in between or listening to the radio link and trying to decrypt or trying to decode all the data and then trying to decrypt based on the encryption. So if you go back to 2011, there's one guy from Belgium called Sylvain Muna. He tried to, no, not he tried, but he actually decrypted a GSM voice call, which was using A51 encryption. And nowadays, this kind of encryptions are broken, and it's better to use 3G or 4G, which have better encryption. So the fourth type of attack is SS7. This is quite popular among state agencies, and so this gives a kind of interface to the attacker to actually locate a particular target or locate a particular phone and track its location, maybe cell level or GPS coordinate level, and try to route calls or try to make a lot of attacks through the SS7 interface. I think this attack started in 2005. So because back in those days there was no proper protection between SS7. But nowadays, there's a lot of awareness about this SS7 attacks among operators. So they try to install firewalls and at least show that this interface is kind of safe, but really not. So the fifth type of attack is denial of service attacks. So where thousands of mobiles are compromised and trying to flood the network with different type of requests. For example, trying to block the channels that are being allocated by the base station. So this is one type. The second type is trying to flood so many authentication requests to the core network so that you keep the server busy and no other users can actually get access to the channel. So these are some type of attacks we have seen in the past. And then, so in all these attacks, the main target or the favorite target was the phone. So always you try to attack the phone, you try to locate the phone, or try to get GPS coordinates from the phone, or try to do some denial of service attacks on the phone. So this was the favorite target for almost maybe last 9 years or 10 years. And so we wanted to see something different, what about base stations? These are also present around us, and then is there something that we can do or try to attack them? Or, the important thing is you can just go there and try to unplug the base station. Okay, you're doing it physically, but there's a chance of getting caught here. So is there any way that you can actually try attacks remotely and without being detected? Then we came across something called self-organized networks, which got introduced into 4G LTE networks. So basically this is nothing but an automatic operation or automatic configure and control of network elements. So you bring the base station to the field, just leave it there, press the on button, and the base station is automatically configuring itself, trying to discover its surroundings, establish relations with neighboring base stations, trying to share configuration details, all these things. So there is no need for the operator to actually send somebody, a personnel, to the field, and he trying to make so many configurations, make setup, everything. So this is kind of a tedious task. And now there are protocols which actually help operators to make this thing simple. So this reduces so many expenses for the operators. So there are protocols for this, standardized protocols, and got released in LTE release 8, the first release. So 2008 itself, these protocols were there. So like I said, to have this connection between the base stations, there is this interface called X2, which got introduced in LTE. And you will see like this interface being extensively used in 5G networks, because we see like so many types of heterogeneous networks, small cells, femtocells, even the macro cells. So there needs to be a kind of interface between them so that they maintain a proper network coverage. If we talk in clear terms, like very, very low level terms, SON is nothing but, it's a software package which is either installed on the base station, or they have something, a centralized control that's controlling maybe 100 base stations. There are different implementations in the market, for example, Ultrasun or Elastic Sun, AirSun. So there are like different vendors trying to develop their own solutions and then try to install them on the base stations. So like I said, it got released in 2008. So most of the base stations which installed in the last maybe 7 or 8 years really have these features present in them. And we found that there were no attacks reported till now. So this could be interesting. Before actually going into the vulnerabilities and everything, I just want to explain like how the self-organized network works in practice. So there could be 3 phases, and this is nothing but, SON is nothing but, it's a control system type. You'll see like why it's a control system. So there's the first phase, which is called self-configuration. So in this phase, the base stations are brought to the field, just left there, and then automatically they download configuration from the core network. Like they have Ethernet links, or sometimes like wireless links also. So it depends on the configuration and support from the operator. So the base station downloads its configuration from the operator and then try to discover the surrounding base stations. Maybe in the surrounding there could be like 5 or 6 base stations or even more. So now the base station has to connect to them. So it has to know the IP address of the neighboring base station. So to discover new base stations, there could be 2 methods. One, the base station has passive scanners. So these are like nothing but cell phones type. They're trying to discover or read broadcast information present in the surrounding. So this will help the base station to actually find new base station. Or else there's a second method where there are cell phones everywhere. So these cell phones are trying to report some kind of measurement details. And in this measurement details, there is kind of information related to base stations. Like, okay, this base station is here and with this signal power. So there are some kind of information that's being sent from the phones to the base station to actually do this self-configuration. So once the base station is self-configured, it has some kind of tables, and then I'll show you what kind of tables in the next slides. So in these tables, there is so much of information like which cells it's or which base stations it's connected to, and then what kind of features the other base station has. So all this information. Physically getting into this base station is possible, but it's big offense. So we are not going that way. And the second phase is self-optimization. Okay, once the base station is there, now it has to automatically, if there is any problem, it has to automatically optimize itself. I mean, it has to continuously monitor its performance, and based on the performance, it has to optimize its settings. Let's say let's say a base station is really having a bad performance. Like for example, it's dropping maybe 20 calls in a minute. So this means that there's a problem in that base station. So it has to correct this. So for that case, there is something called self-optimization. So for the optimization phase, I mean, before the optimization, there is something called, like we just use the name called SON engine. So this is the software which is there. And then this software actually needs some kind of data, like optimize to verify the performance of the network, it needs some kind of data. So there could be like two different types of data. One is internal, the other is external. So internal is nothing but, let's say when a call is dropped, there could be a report being generated in the base station telling that at this particular time, a call has been dropped for this customer, or in this location, the call has been dropped. So this is one kind of report. And as the second method is like external method, where the base station is gathering information from the phones. So the phone also realizes that, okay, when the call is dropped, so there's a signal coverage problem. So it has to create a report. Or maybe if you know about the handover, so if the handover has been failed, so the phone knows that, okay, handover has been failed, and now I have to create a report and save this report. And when the time comes, or when the network is asking the phone, do you have any reports? If the phone says yes, okay, now send me the reports. So the base station is actually, or the SON is actually collecting all this kind of information from the phones, and also collecting information by itself. So all this information is being fed to something called a performance analysis engine. And after some analysis, if the performance is below a certain threshold, let's call it like some key performance indicators. I mean, these are the technical terms we found in so many manuals and products we tried. So if it's below a certain KPI, so it means that the performance is going bad. Let's say like if the performance is good, so it doesn't need to make any change. So if it's good, let it stay like that. So if it's really bad, so there should be something to be done to the network, or the base station configuration has to be changed. For example, like if the base station realizes that, okay, there is interference in the edge of the cell. So in that case, to reduce that or to correct this interference problem, the base station either has to reduce its coverage or increase its coverage, depending on what type of problem it is. So to reduce its coverage, it has to reduce its transmit power. So these are some kind of changes that will be introduced into the network, or let's say new configurations that will be introduced in the network if the performance is not really good. So the third phase is self-healing. So now the base station realizes that, okay, there is a problem in this. So figured out that, okay, there is interference problem. And now it's time to correct this. So either you find like, what's the problem for this interference? What actually caused? And try to fix it. So all these things are happening automatically without the operator's interference. So there's no technician needed for this, and then everything is done automatically. These are some of the technical features that are specified in standards and also present in implementations. The first one is like automatic neighbor relation. So the name itself says that establish neighbor relations. So it means that you establish connections to the neighboring base stations. The second one is like PCI optimization. PCI is nothing but physical cell ID. So each base station which is operating a cell has a unique identity called PCI. It's the physical cell ID. So, and this should be unique for each cell. So sometimes like there could be two base stations due to some misconfiguration problem. They could be operating using the same cell ID. So this really creates some kind of interference, and this should be solved. This should be done automatically also. So this is one of the features present in that. And the third feature is like mobility robustness optimization. So this is to adjust the coverage or the handover settings so that the coverage of the network can be adjusted. So once you adjust this handover settings, then the coverage is automatically adjusted. There could be three different modes of SON operation. The first one is off. So the base stations are just collecting the data, but not actively using that data. So they just store it. Second one is manual apply. So the base stations are collecting the data, but unless the operator verifies that, okay, this new network configuration is okay to be applied. So in that case, the new configuration is applied. In the third case, this is kind of a dangerous mode. So it collects the data and then automatically analyze and then immediately apply if the change is necessary. If a new configuration is necessary, then just apply it without any confirmation from the operator. So the kind of products or the kind of base stations we played with, I think most of them either have manual apply or automatic apply. So we tried to see, like when we did some attacks, we tried to set it in automatic and then try to see how it works. So the main problem we figured out with this self-organizing network is the base stations or the self-organizing network protocols or the logic that's being applied to this network, they're actually collecting so much of information from the phones and over the air. So this information is, it's blindly trusted and it's kind of unverified. So they collect these measurements and then directly use it to generate new configurations. So the problem is like, you gather some information over the air, which could be corrupted and then which could be false information. So this kind of design really creates so many problems, and we see how does it affect the network performance and the network operation overall. So the key question like we wanted to see was like, what happens if we try to operate a rogue base station in a normal network? I mean, operating rogue base station is nothing new, but how do you operate in a specific type of configuration really affects the network operation actually. We know that compromised phones can be used to attack the network, but how rogue base stations can be used to remotely attack other real base stations. So firstly, like some design vulnerabilities. What are the vulnerabilities present? So like I said, the PCI optimization, this is nothing but, okay, here we have a picture diagram with so many cells, adjacent cells, and the cells are controlled by base stations. And each base station is having a different PCI. For example, there is PCI 100, PCI 122, 155. So the thing is like adjacent cells should not use the same PCI. This will really create problem for the phones. I mean, the phones won't be able to decode the signals from the different cells. So that's the reason why adjacent cells should have different cell ID. So let's assume that in some case or due to misconfiguration, two base stations are using the same cell ID. So in that case, one of the base station, like the one which first detects that, okay, there is a collision in between the in this operation. So in that case, the base station which detects this should automatically change its PCI. I mean, it should it should restart itself and then try to take a new PCI. So there's a PCI list. I think usually there are like 504 different cell IDs. And the base stations are free to choose from any one of them. So the base station would automatically restart and then get a new cell ID and then come into operation again. So here we see that operating like when there is interference in this cell ID optimization, so you can easily force the base station to change its configuration. We'll see like how we can exploit these things. The second problem we found was in automatic neighbor relation, like how the base stations are automatically setting up relations with other base stations. Let's say there are two base stations, cell A and cell B, and they're not connected now. Let's say that cell A has discovered that, okay, there is a cell B which is in the surrounding, and if it thinks that, okay, it belongs to my network, and then it has to set up a relation. So the phones are trying to send information to the base station. They try to report some kind of measurements. Okay, these are called as measurement reports in technical terms, and these contain the cell IDs along with the measurement data. So once this is received by cell A, it tries to verify if this information is correct, if this information is legitimate information. Once it's verified, it contacts the core network, finds the IP address of the cell B, and tries to make a connection to that. So once this is done, they are actually set and they can actually share configuration. So like I said, there are neighbor relation tables. Each base station is maintaining some kind of neighbor relation table. And here if we see that there is TCI, and then these are different names that are being allocated by the standard. So this contains like a list of cells, and each of them has different kind of attributes. So the first attribute we see is like no remove. So this means that the X2 link cannot be removed between them. And there is the other one which is called no handover. It means that, okay, there cannot be or there cannot be a handover between them. So these two base, if this box is checked, it means that the base stations are not allowed to make handovers between them. Similarly, there is other parameter called no X2. Like you cannot set up an X2 link between them. The problem we see here is like when a base station A discovers that there's a base station B in the surrounding. So there are no attributes to actually verify if this connection has to be set up or not. So once the base station A receives some information or like discovers that there's a new base station, it automatically sends a connection request to base station B. And then we thought this is a serious problem and we can exploit it. And the third problem we figured was with LTE handover process. I'll just give a brief of how LTE handover process works. So there are two base stations, and then the phone is moving from the source base station to the target base station. So usually when the phone is, let's assume that the phone is on a voice call. And then during the voice call, the phone is continuously reporting measurements, and it says that, okay, now I'm going closer to the target base station. So which means that the phone is going away from source base station, and it's a good time to actually make a handover because it has good signal from target base station. The source base station actually contacts the target base station, tells that, hey, look, okay, maybe in like a couple of seconds, you'll have this phone coming to you. So here are the details of the phone. Make a handover, and then, sorry. So be ready for this handover process. So it talks to the target base station and then instructs the phone to actually go to that particular base station. Now the phone is actually going close to that, and then it initiates a connection to the other base station. So the problem we see is like in the handover command that the phone receives. So the handover command contains like a frequency. Here we see the downlink carrier frequency, and it also contains the target physical cell ID. So these are some parameters that are broadcast in nature. I mean, if you have some radio equipment, you can generate this frequency. And you know the physical cell ID. This is broadcast in nature. So somebody who has passive capability and able to listen to the LTE broadcast network can know what kind of physical cell IDs are present. So these two parameters really control the handover process. And the problem we see is like if all the information that's being received from the phone is considered, is trusted by the source base station, and then instantly given a handover instruction. So we see that sometimes fake cells can be reported in these measurements, and there is no process to verify if they are real or fake. So all these problems we try to exploit in the once we built our setup. Like I said, during the optimization, there is something called handover analysis. So the base or the SON is trying to analyze the handover performance. There could be different type of handover failures, like early handover, late handovers, or handover to wrong cell. So the base station really identifies the handover failures through different reports, like RLF report. This is nothing but a radio link failure report. Or let's say when you enter into the elevator, suddenly the call is dropped. So during that time, the phone actually creates something called radio link failure report because there's a loss of radio link. And this report actually contains the cell identity or the last seen cell identity and the signal strength. Sometimes it can also contain the GPS coordinates where exactly this failure happened. So all these reports are stored in the phone and sent to the network for analysis. When the call has been failed, the base station also keeps a track of this. So we call them as handover reports. And all these reports are continuously monitored, and something called handover success rate is being calculated. Like, this is nothing but the total number of successful handovers to the total number of handovers initiated. So if the handover success rate is going below some threshold, it means that the base station has to create new configurations for handover. So if the handover performance is really below a certain threshold, which is defined by the operator, so in that case, that particular base station can be blacklisted for all handovers. So it means that no more handovers can be given to this base station. So just an overall picture, like these are some types of reports that can be exploited by the attacker to inject malicious measurement information into the network. So the problem here is like this information is not verified by the base station. So they blindly trust this information and generate new network configurations. We found these are some of the functions that are really affect. For example, the first one is like the cell detection and addition process, the cell ID interference detections, then the complete LTE handover process. So all these things are really affected by this kind of attacks. So how we exploit them? So for this, we built a hardware. So here we don't really need a full-fledged LTE base station. We just need something very tiny. So for that case, we used a Lime SDR. Maybe some of you might be aware of it. So this costs like maybe $150 or $100. And then we used a small PC so that we compile SRS LTE software. So these are some of the open source software that are available for simulating LTE base stations. So we use some of them, but you don't really need the full capability of a base station. So it's sufficient that you just transmit one broadcast signal, which is nothing but SIB1, maybe if you're aware of a bit more details of LTE. Also, like in this case, we don't really need any interaction with the phone. So it's just sufficient that this setup broadcasts a particular signal and it's being detected by the phones. So we tried with different kind of amplifiers, like with the kind of setup you see here, like the default antennas, maybe 50 meters or something. This is good enough to actually cause a lot of damage. So for testing, we use different type of SON base stations from different vendors. I don't want to put any names, but also we tried these attacks in practice. I think most of them really work. So, okay. So the only thing this setup does is like it tries to collect all kinds of cell identities in the surrounding and try to broadcast one of them, or the best suitable one. So how we exploit the network, and then the first one we try to exploit the X2 signaling. So let's say we have a network. Below you see the hexagonal cells, and then there are real base stations which are operating different cell identities. And then each base station, like I said, it's maintaining a neighbor relation table. So if we see the base station PCI 100, it has a neighbor relation with 122, and there's a different cell called 109. I didn't show it in the picture, and it has some attributes for that. So now what we see is like there's a new base station, or no, not a new one, but there's a rogue base station, which is trying to impersonate the cell identity of 133, which is like distantly located from PCI 100. So in reality, there is no point of having X2 connection between PCI 100 and PCI 133 because they're practically very far and they don't need to exchange any kind of signaling or any kind of handovers. So generally operators don't connect base stations which are quite far away. So, but what happens in this case is like I said, there is a lack of authorization mechanism to actually verify if this connection is needed or not. So what we see is like once you impersonate this base station, PCI 100 would establish a connection with the base station which is quite far away, and then try to add it into the neighbor relation table. So in this way, if you try to operate rogue base station with so many different fake identities, what happens is like you try to flood the neighbor relation table of PCI 100 and you fill with bogus data. So sometimes this really affects for handovers, because a handover can happen to a wrong cell or a non-existent cell. So these are some of the problems with lack of authorization of this X2 signaling. So the second attack we tried was like, how do you remotely kill and restart a particular base station? Like I said, there should be unique PCI to each cell. Let's assume like this is a typical configuration. There are different PCIs, unique PCIs in a particular location, and you try to operate a rogue base station that's actually impersonating all these three identities. So what happens is like these real base stations detect that, okay, there is a adjacent base station which is trying to use the same identity as mine. So what I have to do according to the S1 protocol, I have to select a new PCI. So to select a new PCI, because like this PCI is nothing, it's a physical layer parameter. So it's not a higher layer parameter. So it really affects the signal, the transmitting signal. So for that, the base station has to restart themselves. So what happens is like they restart and then get a new PCI. So in our experiments, like roughly it takes like 7 to 8 minutes for a base station to restart. Maybe there are some very tiny base stations, micro cells, which could take maybe 4 or 6 minutes to make a restart. But some macro cells really take a bit long time. So during that time, when a base station is restarting, sometimes like the phones which are already connected with this base station are transferred to a 2G or 3G base station. So which makes the phones more vulnerable than staying on a 4G network. So the third attack we tried was handover hijacking. So this handover hijacking was not possible with IMSI catchers in 2G and 3G. Because with my interaction with so many IMSI catcher like makers and all these things, like they had problem with catching guys who are already in a call. So, but I see that with LTE, it could be much easier. I mean, this is not really nice because with better generation, like when you go to the next generation, the security should be better, but should not drop off. So how we hijack the calls? Like, let's say there's a phone that is in an active call with the base station with PCI 200, and there's an adjacent cell with PCI 100. So now the phone is actually constantly reporting measurement information. It also reports the measurement information from PCI 100. But since it's very far, there is no handover taking place. But now you see that there's a rogue base station which is coming up and trying to spoof the same cell ID of a distant base station. So now what happens, like in the measurement report that's sent by the phone to the PCI 200, it thinks that, okay, it's going close to PCI 100, and then it would initiate a handover. So PCI 200 would send a message to PCI 100 telling that, okay, this phone is coming close to you, and let's make the handover handshake and everything, make the parameters ready, and this would initiate a handover command to the phone. I mean, in this case, the phone was actually referring to the rogue base station, and the real base station was referring to the other base station, which is also located far away. The problem here was like the base station with PCI 200 did not really verify the kind of measurement information sent by the phone. So this leads to the problem of handover hijacking, where the phone would now contact the rogue base station. It would end up with the rogue base station and try to continue the call. But due to the lack of the security keys and due to lack of proper parameters, the rogue base station cannot continue the call. Let's assume that if the rogue base station has the keys and everything, let's say this is a state-sponsored attack or something like this, and in that case, the call can be continued, and then the attacker has all the capability to listen to the complete conversation. In this case, let's say like there's no proper keys, and then the call would be dropped. So when the call is dropped, the phone would create something called radio link failure report, like I said. So, and this report is stored in the phone, and this report actually contains like different measurements and the cell identity. And this cell identity is nothing but the cell identity of a legitimate cell, which is being spoofed by the rogue base station. And this information will be sent to the real network for analysis in a later case. So assume this kind of failures happening maybe like 100 times or 200 times. So there are different radio link failure reports, like 200, which are reported against a particular legitimate base station. I mean, here there's no problem in the real base station, but by operating a rogue base station, you show that there's a problem in a legitimate base station. So by this, what happens, like when these kind of reports are being generated against a particular base station and the performance is going below a certain KPI, so there could be two options. One, that particular base station has to be handover blacklisted, or in some cases, that particular base station has to be shut down because it's really doing bad and it's dropping all the calls. But in reality, there is no problem in the legitimate base station. But by operating this rogue one, you showcase that there's a problem in that. We tried in practice, and then we see that it's sufficient. Like within 5 seconds, you can actually drop all the cell traffic. Maybe if there are 100 calls, 100 active calls going on now, I mean, it doesn't matter if it's a call or a data traffic, like everything would be dropped. So maybe once the base station has realized that, okay, it's shut down, now the operator has to maybe manually initiate some new operation, like trying to figure out what really happened to that base station. But of course, like in the end, he will realize that, okay, there's no problem in that, and it would be back in operation again. So talking about the impact, so we see that the calls would be dropped, also the data connections would be dropped, and there would be poor network coverage and interference problem because there would be misconfigurations of this base station. So to avoid that, it's really hard for the operators to actually detect in this stage because there are not really any kind of mitigations available for this. Because here, the attacker is just operating a base station which looks similar to the real one. He's not trying to jam the network. I mean, operators can actually detect jamming because for jamming, you really need a high power signal. But to operate a base station, you don't really need any kind of high power signal. It's sufficient that the phones detect this signal. So maybe 2 watts or 3 watts is really sufficient to cause a big damage. Like typical base stations really have like 40 watts. So that's the scale of the attack. For the operators, it would be a huge revenue loss, and then of course definitely complaints from different customers due to the drop of calls, and also poor network coverage due to the poor network settings. And the other thing that would affect the subscribers is, like, most of the times you see that the phone would be switching to 3G or 2G network. So you're making more vulnerable to the attacks that are applicable to 2G or 3G generation. Also, these attacks really need time to heal because SON is like a control system. So it observes the behavior of the system for a certain period of time and then initiates a new configuration. So I just provided a link to find the complete information regarding this work. Maybe if you are interested, just see this link for more information. So the security status of this, we tried with several phones, and all the phones complying to this release 8 and above specifications are really affected with these attacks. Also, we tried various products, I think 4 different base stations with SON capabilities, and trying to switch between manual and automatic features. All of them are like affected, and we tried to inform them about this. We had a big discussion like how this affects and all these things. We tried these attacks, and we discussed with 2 European operators and also disclosed with this GSMA, and I had so many questions from operators like, okay, if this is the case, then what? Then so many questions. Sometimes, like, they said, even I had some questions like, what would you do in this case? So they said, like, okay, if the attacks are like mounting up, they would try to switch the network to less automation. Maybe they would put it to the manual mode or try to put the SON off. Also, they said like, then I asked like, what do you do for the PCI problem, like where the base station is restarting itself? They say maybe sometimes like they make this restart of the base station during low traffic periods, maybe in the night or midnight or something like this. And they said if the base station is really doing bad, they would really unplug this and try to compensate with different available base station. And we see that it's really difficult to add mitigations. And then for this, because these protocols belong to LTE release 8 and we are in the phase of LTE release 16. So at least for 5G, they started to add mitigations. And then we are working with the GSMA to try to generate some kind of guidelines document for the operator so that they could use to properly configure the network in case if it's a self-organized network. And then also try to deploy some kind of protection mechanisms against rogue base stations. I mean, it's really hard to stop somebody from operating a rogue base station, but at least to detect them and then trying to stop their effect is really something we are caring to do. We look for different solutions. Okay, the first obvious solution would be, since you're talking about broadcast messages, so this was a huge discussion also in 3G, 4G, and also in 5G. Why not use signed broadcast messages? Why not use signing methods? But this would really create a huge, I mean, it's not easy. It has a complicated design because like once you have this kind of solutions, the phone has to hold thousands of base station certificates because whenever it moves to a different location, it has to authenticate the base station based on the certificate. So it's not a practical solution for the phone to hold thousands of certificates, base station certificates. Then the second easy solution would be to verify the content or verify the kind of information that's being received from the phones. So this is the main problem. So why don't you verify the kind of measurement reports and radio link failure reports that's being received? You maintain like your own database and try to cross-check what's being received and try to solve this problem. This could be an easy one, but still you have to make a lot of changes to the protocols, LTE protocols. So then the third one could be try to add intelligence to the self-organizing network. So like I said, this is the software package, so it's easy to make changes. Also, why don't you like verify the content that's being received in the SON? Then the fourth one, we are actually working with a vendor trying to build some kind of baseband features inside the baseband. I have heard like so many solutions that work on Android and also on the, maybe not on the iOS, but on the Android, trying to build secure phone and trying to prevent this from rogue base station attacks or IMSI catcher attacks, or trying to shield the phone so that it's not visible to any kind of RF in the surrounding. So these are some of the solutions that I saw, but we thought, okay, it's also possible that you do this inside the baseband because you have more control on the radio than sitting on the Android. Yeah, some key takeaways are from this, like SON protocols have been with us like for the last 10 years, and it's really, these cannot be trusted, and these are actually sitting in the operator side, so we have less access to actually play with these protocols. So, but somehow we did this, and then we found that these protocols cannot really handle attacks from rogue base stations. And the kind of, because they really impact the operation of the network, so they should be resistant against any kind of attacks or this kind of simple attacks. Like we saw a simple device that's costing like $200 is capable of modifying the network configurations and putting it off. So since these protocols are automatically operating, so they lack some kind of verification mechanism, and we try to propose this verification mechanism, and it's up to the operators whether to choose any kind of solution, whether you go into adding intelligence to the SON, or you try to change the protocols, LTE protocols, I mean. So yeah. So this is about problems in SON, and then yeah, I'm open for any questions. Thanks.
Thank you, Ataif. Are there any questions from the room? No, none whatsoever. I think they will come after when you get off the stage. He'll be around. Thank you, Ataif. Give it up.